Hello, this is Jim Schnabel. I'm giving the talk. This is number 6 in the series on the Principles of Biochemistry by Albert Lehninger, 7th edition. Today we'll be discussing water ionization, acid bases, and address the Henderson-Hasselbalch equation. Most of these are algebraic constructs, so if you think of these algebraically, you can fill in many of these problems that exist. And I would certainly point you in that direction. We talk about water ionization to give a foundation. In biological fact, much of the impact of physiologic pH is derived from other substances, predominantly bicarbonate, in the physiologic system, which shifts the physiologic pH slightly alkaline. And we use water as a model because it forms sort of the foundation. In biological systems, we really don't see the imposition of strong bases such as hydrochloric acid and sodium hydroxide in biological systems, but they are used in biological experiments and laboratory extractions, and the imposition of those compounds, in fact, will cause denaturation of proteins. So these are done on a very limited way. Most of our work is done with weak acids and weak bases, and as such, they are compatible with acid-base chemistry. But we start with water because water is sort of the model that we use for this. So at any given time, there's very little of a body of water, volume of water, which is particularly charged. But we do have fleeting representation of hydronium atoms, and hydronium is an H3O, so they're slightly positively charged, and the proton is the dipole of the proton is transferred throughout the solution. But as a function of this solution, very little component of this has a charge, but is sufficient to conduct electricity, to conduct charges, and you can measure this. When we look at free protons, they do not exist in solution. And to look at the ratio of this, we have what's called the equilibrium constant. For water, we look at the water constant, which is Kw, uppercase K, lowercase subset to W. And that number is 1 times 10 to the minus 14th. If you take the log of these numbers, you equilibrate hydrogen, proton, and hydroxyl ion at equilibrium, those numbers are going to be equivalent, and minus the log of the concentration, which is 10 to the minus 7, becomes 7 as a positive integer. So this is the way we calculate pH. In actual fact, this constant is equivalent to the proton and hydroxyl divided by the concentration of water, the molar weight of which is 55.5 molars. It would be that many moles that you would have in 1 liter. It would be 55.5 grams of water in 1 liter divided by its gram of molecular weight. So that molecular weight is 18.05, and then you get 55.5 moles is the concentration. That number is included in the calculation, and so we're just looking for this water constant. We're just looking at the product of the proton and the hydroxyl group. So as I said earlier, blood has a pH of 7.4. And if you have acidosis or alkalosis, you're getting deviation from this, and you have physiologic problems with this. Acidosis is much more common clinically. You get that with the diabetic ketoacidosis, and this is a dire emergency when it develops. The main blood ion that is used, the main plasma ion, is bicarbonate, and that shifts the pH slightly alkaline to 7.4, and that's a physiologic number. If you deviate from that, then you get coagulation of proteins and malfunction and non-function of all the various constituent amino acids or enzymes and other groups that require a certain pH in order to function effectively. We discussed strong acids and bases. They're not really a player here. Things like hydrochloric acid and sodium hydroxide would be used in vitro in chemical extractions, but they're not really a player in terms of the acid base that occurs in physiological situations. It is critical as we get into the pathways that we look at Lewis acid and Lewis base. We will review the pathways using that to dictate Lewis acids by definition are electron pair acceptors, and Lewis bases are electron pair donors. And these are used to fulfill the orbitals, the s orbital, the p, the d, and if possible the f. But you really don't really go much beyond the p or rarely the d orbital in biochemistry. And knowing the electronegativity charts where the more rightward and more superior, in other words, the more upper right you go, as opposed to the lower left, the electronegativity increases, which is why fluorine, for example, being at the upper right of the periodic table, is so incredibly reactive. Weak acids and weak bases will ionize incompletely, whereas strong acids and strong bases ionize completely. And the weak, incomplete ionization is what's characteristic of the equations that we'll be reviewing in this particular section. You get conjugate acid-base pairs, and they convert to bases and protons. So any substance that you've got, if you put a strong pH or a very low pH, there are going to be no negative charges. As you increase the alkalinity of the surrounding solution, you get more and more negativity charges, and those are related to the pK values that are encumbered, particular when you've got atoms or molecules rather with more than one potential charge on them. So again, we look at acids losing protons, bases accept protons, and this is the way we go into this. Ionization constant is the product of the concentrations which exists when you've got proton, rather the acid and the conjugate base over the concentration of the unionized total concentration of acid that's existing. And the Ka is proportional to the strength of acid, and as modeled earlier, the pKa is equivalent to the negative log of the Ka, the activation, the ionization constant. Practically speaking, we can look at the pH as a mathematical construct. So the buffering region is generally plus minus 1 pH over the electronegativity or the pK value that occurs here, and this is where the negative these charges are offset right here, the negative and the total here, whereas you get no negative charge at this point, much fluctuation of the pH with even small amounts of hydroxyl added as equivalents, and then the pH buffering region over the vast expanse, and then as hydroxyl is added, and you get more and more movement of this log curve. It's a log curve, so this difference here is going to be about 100 in either direction, 10 here and 10 there if you plug in the actual concentration numbers. Once you lose that, then the number blows up, because this is a log curve, and that should always be known. So a buffer is a mixture of weak acids and conjugate bases, and the Henderson-Hasselbalch equation is a re-expression of the ionization constant of an acid. So again, if we look at the ionization constant equivalent to the proton concentration multiplied by the concentration of the conjugate base divided by the total concentration, pH is a negative log of H, pK is negative log of Ka, And if you you can do an arithmetic construction of this with this substitution, and you get pH is equal to pKa plus the log of the conjugate base over its total concentration. And by plugging in the numbers, you can derive pH as a function of the ionization constant and the varying concentration of the log function here. So in the biological buffering systems, you have phosphate buffer, which is H2PO4 negative. And the pKa for that is slightly acidic at 6.86. Bicarb, as I said, the acid pKa is 3.57, and that low pKa is mitigated because you do have carbon dioxide dissolved in blood. So the combined pKa is calculated at 6.1, and for the buffering system of bicarb, this log of the conjugate base bicarb over the carbonic molecule is the carbonate molecule is 7.4. And again, these are all derived from mathematical operations, and you can look at it in terms of mathematical constructs. So if you're given the concentrations, if you're given the pK and pKa value, you can plug in and get the numbers in particular order that you wish to receive them. So that's a brief overview of this system for biological buffering, the pK and the ionization constant. Thank you.